Okay, so now it is starting to record. Good, good. Are there any other questions? If not, let's. So I actually posted this homework problem. You may have noticed. I will add some more to it. The problems are a little tedious, where you have this manipulating these retarded potentials. For example, if you want to get E and B from these, it is pretty tedious and difficult. You have to be very careful about how to take gradients and curls and so on, right? So it's a good idea to try to do it, but it's also something which is extremely time consuming. It's best done on your own, and I'm sure almost everyone will make mistakes. I mean, the key idea is to have patience and to have one of the books that does it in detail, for example, Griffiths or Jackson or something. Okay, but we are going to use these. We are not, the course is really not about these retarded potentials, deriving and showing all these. For example, you want to go from phi and A to E and B, right? I had written down this expression for where did it go? Right, so maybe even before this, right? So I had written down this E and B. These are actually derived from those retarded potentials, but it is actually very tricky and algebraically very tedious to go from those retarded potentials to here. But one should actually at least go through and try to see how these may come about. It's done in Jackson and in Griffiths, but I will just, we will just use the final formula. We haven't really derived it, but I encourage you to try to go through it. You may have done it in a previous course on E&M. Okay, let's go to today's class, which is.
Sir, I have one question regarding the tutorial. Can I ask it now?
Tutorial, that is
I think the homework, sorry.
problem.
Homework.
Yeah, let's ask it in the homework, in the tutorial session itself, unless it is, very short.
Yeah, it's a short technical thing. I mean,
Okay.
you wanted to find out the degree of polarization. Should we use the Imax minus Imin formula in question number 3?
Yeah, degree of polarization is Imax, Imax minus Imin divided by Imax plus Imin, right? So basically, degree of polarization is defined as the intensity of polarized radiation divided by the intensity, total intensity.
Yes.
Okay.
So,
Yeah.
okay, that is the formula. Okay, thank you.
Yes. Yeah. Okay. So let's go to today's class. And I encourage you all to keep reading the book. The book is actually very nice. It's at the absolutely perfect level for this class. But as I said, the basics can actually be looked up from more traditional E&M books. Have you, have people read the book, Rebecca Enlightenment?
Sir?
Have you guys read some of this? Yeah.
In the
I have
first
another.
chapter we had.
Yeah. So I really like. It's very succinct. It's not very wordy, but it does assume that you have done E&M properly. So, and I think that's true for most of you guys. But if that is not true, you guys should keep revising stuff from the more introductory books. Okay, let's get started with today's.
Sir,
Yes.
I have
Yes.
another question as well.
Yes.
So in the book Rebecca Enlightenment, there's
Yes.
a picture depicting the geometry and emission pattern for dipole radiation. Could you
Yes.
please explain about it? I didn't understand
Okay.
much from that picture.
Okay, so this is figure 3.5, I guess, right?
Yeah, yes, sir.
Okay, so let's see. Let's actually talk about that. So so power radiated by a dipole. right? So we know that, you know, we mathematically derive this power formula as, you know, this is dp d omega. So this is power in some direction theta. This is given by d double dot square. So this is very much related to the Larmor formula, and sine squared theta divided by 4 pi c cube, right? E square a square by c cube. It's very similar to that. I mean, that's the total power, but this has angular distribution. So this figure 3.5, actually, let me just first draw it. Right, draw back, undo. So figure 3.5 draws something like this, right? It has these directions, right? So this is the direction of d double dot, which is the direction of basically dipole, and this is some general direction n hat, right? And this angle is this capital theta. Okay, so, and you know, basically what this formula says is that the power radiated in this direction, capital theta, is given by this, right? It's obvious, right? If you're looking from here, the acceleration is along the line of sight, and if you recall, your electric field in radiation was proportional to beta dot perp, right? The acceleration component perpendicular to the line of sight. So if your particle is accelerating along the line of sight, this will give you 0. So that's the reason for this sine square theta. Now this figure 8 is basically nothing but so, you know, you are here, this angle is theta. So this is nothing but a locus of so this is your direction, this is your angle, capital theta. Now what you say is, I will draw, so when theta equal to 0, I will, you know, basically what you're doing is you're making a locus of sine squared theta equals the constant. Let me see, you know, I've actually never, I mean, these types of patterns were very, very popular some, you know, long time ago, because, you know, these gave a good intuitive feel for where the power is. So, you know, if you look at in this direction, the distance is 0, right? It's sort of touching at here. So there is no power radiated here. If you go here, this distance is the farthest, so there's maximum power here. And along this direction, it's little less, and so on. So this length of this this line is actually proportional to power, right? So this is some sort of a polar diagram. So just a second. So this is your power equals some constant times sine square theta. If you want to draw this as a function of, this is actually capital theta. Now, right, so here in this direction, P is equal to 1. Here in this direction, P is equal to 0. And, you know, so basically what you're doing is, for a given theta, you are actually marking this, right? Some constant sine square theta and some constant sine square theta. And, you know, it's sort of symmetric, and it sort of goes like this, right? You get what I'm trying to draw? So this angle is theta, and the size of this is the power that you get. So you get 0 power and theta equal to 0, and you get maximum power at theta equals pi by 2, and it's symmetric, you know, plus theta minus theta. So this gives you like a beam pattern, right? If you have a dipole which is oscillating like this gives you a visual feel for that. There will be no radiation coming out in this direction, and maximum will come out in this direction, and it's mathematically given by this. In fact, we should actually draw it, just use whatever Python or whatever, and make this plot of power as a function of, this is really not power as a function of theta, because theta is represented in the plane, right? It's not like P as a function of theta, right? This is more like theta is represented in space. So that, for example, if you have a circle, right, a circle would be R equals R naught, right? So this is independent of theta. But if you have something else like an ellipse, where you can actually write function of R and theta equal to 0, and that will draw some shape. In the same way, these are like this is R and this is theta, right? So these are like polar plots. I don't know, these are perhaps called polar diagrams. I really don't know what they're called, but this is the idea. Get it?
Yes, sir. I got it now.
Good. Yeah, in fact, I should give a homework problem to draw it. Everyone knows a little bit of plotting and so on, right? So you can actually use Python to draw this. Okay, let's go get back to the class. Okay. Okay, so we actually talked about dipole radiation, just as in electrostatics, right? We have multipole expansion. In radiation too, we can expand the radiation field as a sum of a dipole, quadrupole, octopole, and so on. Okay, and the mathematics is very, very similar. If you recall, in our dipole expansion, what do? You have like some source distribution of charges, and you're looking from far away, and you are actually, basically approximating this as an expansion, right? You assume that this is small, and you write it as R1 minus R prime by R, and you just do the dipole, so you get multipole expansion. In the same way, we can do it in radiation, but right. So in case of radiation, you have to have dipole, otherwise. Monopole does not radiate, right? Because if you have a monopole, if you have a charge, charge has to move, and a moving charge will have a non-zero dipole, or accelerating charge will have a non-zero dipole moment. So, I'm just sort of telling this, we are not going to do it, because, most of the time, dipole radiation is the most dominant part of radiation. Okay, but not in all cases, of course. Okay, so let's go to. So there is, it is discussed in the book. It's sort of mathematically. You can actually just do this. It's very similar to multipole expansion in electrostatics, for example. Okay, let's go to where we want to go to, which is Thomson scattering. So Thomson scattering is the phenomenon of scattering of light, scattering by free electron. You can actually treat any charges, but electrons are the lightest, and they are the most efficient emitters, as opposed to, for example, protons. They are heavier, so they are not as easily accelerated. So we'll treat electrons, but the formulae apply to all charges. So basically, this is the setup. Let me draw it. So you have some direction. You have linearly polarized radiation. You have linearly polarized sinusoidal waves being incident on an electron, which is sitting here at rest, and because of this electric field, it sort of starts oscillating, right up, because there is electric field which is oscillating at its position. So, and we are assuming that the velocity of these electrons is much less than c. This is true if the electric field which is incident is not very strong. Okay, so we know the Lorentz formula for the forces on the charges is equal to Q E plus, right? And we also know that for an EM wave in vacuum, we know that B is equal to E. The magnitude of magnetic field is equal to magnitude of electric field. So if E and B are comparable, but if V is much less than C, you can actually ignore the magnetic force relative to the electric force. So, so how is the motion of this electron described? So let's see, M R double dot. So this is just MA. MA is equal to the force which is acting on the particle, which is E epsilon hat. So this direction is.
Sir, what are the assumptions under which we are assuming V very, very less than C?
Basically, the electric field of this source is not very strong. If electric field is very strong, then it can very quickly accelerate it to close to C.
Okay, thank you.
Okay, so that's one assumption. So V by C much less than 1. This is true if E is sufficiently small. Basically, you cannot apply it to high intensity lasers, for example, but you can apply it for light coming from the sun and so on. They're not extremely intense radiation sources. Okay. If electric field is strong, what happens is you get figure-8 motions, trajectories of these electrons, right? And otherwise, it's just dipole oscillations. But we'll not treat this. This is mathematically tedious, but this is the most useful case that we usually encounter. Excuse me. Okay. So E dot. E dot sine omega dot t. So this is the force. This epsilon hat is the direction of polarization of this linearly polarized line. So we are considering linearly polarized incident radiation. Okay, so these electrons will oscillate, and we know that oscillating electrons are like accelerating electrons will radiate dipole radiation. So if you consider this n hat, right? So this is n hat, this is k. So k is the direction of incident wave, n hat is the direction of scattered wave, and this is basically the angle capital theta that we have been using, right? This angle capital theta is between acceleration direction, right? This is the acceleration direction and the direction of observation. This is your R, this is from where you're observing. Okay. So this is your equation of motion, MA. This is the force EE. We are assuming the phase that at t equal to 0, electric field is 0. So we are just fixed at this position. So the electron is fixed at this position. It only experiences force in the epsilon hat direction. So it's just going to oscillate. We know that. It doesn't move along the direction of k when V is much less than C. Okay. and we know that, let's multiply both sides by E, so this becomes this, and we know that ER is your dipole moment. So your D, the dipole moment, is nothing but E squared by M E naught sine omega naught T epsilon vector. And this omega naught is this frequency of this oscillation, right, of the incident field. So the charge will oscillate at the same frequency as the incident radiation. So this is your D double dot. What is D? I mean, this is periodic sinusoidal motion, so we know that D is nothing but minus E squared by M, E naught by omega naught squared sine omega naught T epsilon. So your amplitude D naught of the dipole is E squared E naught by M omega naught squared in the direction of this polarization of the incident light. And we now know, we know the dipole formula. We know it's written here, right? So we know that. So we know how much power is emitted along some direction theta. So let's just write that. So dp d omega is equal to, that's the formula, and this is my d, and this is my d double dot. So this is E squared E naught by M whole squared sine squared omega naught T sine squared theta by 4 pi C cube. And if we sort of, normally when we are measuring intensity and power, we average over the time. So this sine square omega naught T will just give us a half. So this we can actually just, we average it, and this gives us a half. Okay. So what do we have? We have, so this is equal to e to the 4 E naught squared by 8 pi M squared C cube sine squared theta. This is your power in this particular direction. What about the total power? The total power is nothing but this integrated over all solid angles. So that's the total power. So this is the power scattered. Basically, this is the power due to these oscillating dipole in some direction. And this is the total power if you integrate it over all angles. And so basically we have, this n hat is sort of, this is sort of like a z-axis, right? And n hat, you're symmetric with respect to this direction. That's like a phi. So what do you get? You get e to the 4 E naught square by 8 pi M square C cube, and sine squared theta right, that's just so that's just sine squared theta average over all solid angles times the total solid angle, which is 4 pi, right? That is just this. So sine squared theta average over all solid angles is what? It's 2/3. And actually cos squared theta average over all solid angles is actually 1/3. You can actually see that. So what do you get? What you get is e to the 4 E naught squared by 3m square c cube. This is your total power, which is emitted by this oscillating electron. So what about, so if you have an incident radiation, the Poynting flux of that incident radiation is, average flux is what? This is just, right? If E naught is the amplitude of electric field, this is your Poynting flux of incident linearly polarized light. Okay. Now we can actually define, this dPd omega, the power going in a certain direction, in this particular solid angle. This is equal to nothing but S, the average incident power, times d sigma d omega. So this is how you define this quantity called differential cross section. Differential cross section d sigma d omega. This is how, so basically the power radiated in some direction theta is equal to the incident flux times the differential cross section d sigma d omega. Now you see, this is energy per unit area per unit time. This is energy per unit time per unit solid angle. So this has to be area per unit solid angle. So the higher the differential cross section is, the more power will be scattered in that particular direction. And this is actually a definition, right? It sort of is like size of the scatterer in some sense. Okay. Now this is the scattered. This is dPd omega, and this is incident Poynting flux. So all we have to do in order to calculate d sigma d omega is take the ratio of this and that. So what we get? We get d sigma d omega of polarized, linearly polarized light is equal to, we are just taking the ratio of this and this, which is this and this and that. And what do we get? We get e to the 4 m square c4 sine square theta. Okay, so this is your differential cross section, and this is sometimes called, written as this, right? And the cross section has a unit of area, so we can actually define a length like this. Okay, and this length, this R0 is nothing but E squared by mc squared. Do you see, can someone give me an interpretation of this, in terms of like simple physics? mc squared is like a rest mass energy of an electron, for example, right? So what you're saying is this rest mass energy, and E square by R0 is like electrostatic energy, right? So what you're saying is that all the rest mass energy of this electron is because of the electrostatic interaction. So this is that interpretation. You're just balancing E square by R with mc square. So this is called classical size of an electron. I mean, it's dimensional analysis. There's no other fundamental constants here. And if you plug in the numbers, this is about 2.8 times 10 to the minus 13. centimeter. Very small, of course, much smaller than the size of an atom, which it should be. In fact, if you calculate it for a proton, it's even smaller. And that's understandable because protons are even worse at scattering radiation because they're heavy and they are not accelerated as much. Okay. So this is your class. So so this is called this phenomenon is called Thomson scattering, and this is classical size of an electron. And this is the pattern. See, one thing that we have to be careful about here is this theta, this capital theta, is the angle between the direction of acceleration and the direction where you're measuring the scattered light. Okay, it's not this angle. And basically what I'm saying here is that this direction, right, in the phi direction, you have symmetry about this direction, right? Whether you measure radiation in any of these phi's, you will have the same power measured. But that's not actually true for measuring the power along the k direction, right? Because here, if you go in the phi along the k direction, this is in the plane of acceleration and n hat and k, but these are not symmetric. Are you getting the point that I'm trying to make? So the direction of axisymmetry is with respect to the direction of acceleration, z, this d double dot. So this is your z axis of a spherical coordinate system that you choose. Okay. So this is this is your differential cross section. What about sigma? Just like this, you have total power equals flux times the cross section, or this is how you define total cross section as opposed to differential cross section. Or you can take, say, sigma equals d sigma d omega, right? So that would be r naught squared, and so that's sine squared theta and d omega, right, over all solid angles. And this is nothing but r naught squared times 4 pi times the average of sine squared theta. And I told you beforehand that sine squared theta averages to 2/3. So this is equal to 8 pi by 3 r naught squared. This is your sigma total, integrating over all angles. And this is Thomson scattering cross section. The other thing to note is that scattering cross section is independent of frequency. It does, whether you have incident radiation at some other frequency or some large or small frequency, it's the same. Thomson scattering is independent of the frequency of the incident radiation. And if you plug in the value, you get, this is about 6.7 times 10 to the minus 25 centimeters squared. Right, and so just a sec. Okay.
This is for electron, right?
Yeah, this is for electron, but you can apply it for even for proton. The problem is our proton is even smaller. It's not as efficient radiator, right? The proton. So if you, for example, if you do this for a proton, what do you get? You get about 2,000 times smaller value, which is 10 to the minus 16 centimeter. The cross section will be 2,000 square times smaller. So
2,000 square times. Yes.
Protons are 4 times 10 to the power 6 less in scattering than electrons, right? Because electrons are light, and because of that they are accelerated much more, right? Because acceleration is E by m, right?
It's
Yes.
1 by
Sir, I have a question.
Yes, please.
Sir, you said that it is independent of means the frequency you are using to
The cross section is independent.
Yeah,
But
sir.
but the frequency of the scattered radiation is the same as omega naught. It's just the cross section which is independent. So these electrons will be oscillating at the same frequency, and they will also emit at the same frequency. So if this is omega naught, the scattered light also varies at omega naught. But the cross section is the same. So if you sort of have radiation which is like say 10 times higher frequency, the fraction of light that you get in this direction will be the same in the two cases. You get it? When I say that the cross section is independent of frequency. I mean, although the scatter light will obviously be oscillating at the same frequency as the incident light, but the fraction of light that appears in this direction will be the same in the two cases. This is not true always. For example, for Rayleigh scattering, there is a very strong dependence on frequency, right? Okay. When does it break down? It breaks down. This simple treatment breaks down when h nu, the energy of the incident photons approach the rest mass energy of electrons, right? Then you have Compton scattering, which is inelastic. Basically, inelastic. But here we are saying that the radiation and the incident photons have the same frequency. But when the energy of the photons are comparable to the rest mass energy of the electrons, in that case, it's inelastic, right? And the frequency that comes out is smaller than the frequency that's incident, and that's Compton scattering. So basically, you're not treating high energy radiation. You're treating this is 0.5 MeV. So when you go to X-rays, your Thomson scattering is no longer valid. You have to worry about the energy losses due to energy exchange between electrons and photons. So in X-ray regime, which is you have to be concerned about that. Okay, so what about the polarization of the scattered radiation? Let's go back to this diagram. What about polarization? What is the direction of this? Is just dipole oscillation. If you recall, polarization or the direction of the electric field is in this direction, right? It's in the plane of acceleration and the direction of observation. So this is the direction. This is how it will be polarized. This light will be polarized in this direction. Okay. So when you're right, this is the direction of polarization, and for example, if you're right, so let's take some simple cases. So if your theta is equal to 0, for example, what happens in that case? You're accelerating in this direction, and you're also seeing in the direction of acceleration. So your power is equal to 0. Right, that's also given by the sine squared theta. So if theta equal to 0, you don't see any power. So if you measure here, you will see no scattered radiation. If you will see no light basically. if you're looking towards minus z hat direction. On the other hand, if you're looking at minus k hat direction, what would you see? You will see, you know, this. You will see this whole oscillation because beta perp is the full acceleration, and you'll see a maximum. And in that case, the scattered radiation will also be polarized in the same way as the incident radiation. So this is in the plane of n hat and the direction of acceleration. Now, if you're looking like down this, let's actually choose our axis x, y, and z. So that's z. This is, let's say, x, and this is your x, y direction into the board. So if you're looking, say, from y hat direction, what do you see? If you're looking towards the y hat direction, you will see radiation in the same way as if you're sort of seeing from the x direction.
No,
right,
sir. I mean, I mean, there will be 8, right? 8 structure. I mean, if from y direction, because
right,
the
so that
peak is around x cap.
8 direction is like this, yes.
Yes, yes, along x cap.
This, right. But this 8 is also rotationally symmetric. Sorry. Right. So this 8 is about the z cap.
X cap, right?
Just a second. This is the direction of acceleration. This is the direction of acceleration. Right. So this is correct. Yeah, what I drew is correct. You will see maximum light here, and you will see nothing from that direction, and that's also easy to see because the acceleration is along the line of sight. Okay. But if you are sort of seeing in the y hat direction, your acceleration is still perpendicular, right? So if you're sort of seeing from outside this plane, you will see this acceleration. So I think you will, you know, if you're watching in y hat direction, you should see non-zero radiation, won't you? Now I'm a little confused. That's the direction of acceleration. Right. So this, okay, got it. So this figure 8 that I drew in the XZ plane, you can actually rotate it about the Z axis, right? That's the direction of symmetry. So you'll have this 8, which is sort of like a dumbbell, which is symmetric in the phi direction, which is about Z hat. So you get, so this is sort of, you will see maximum along Y hat as well, right? So the Y hat electric field or the power received in Y hat direction will be the same as in the X hat direction. You see what I'm saying? This figure 8 is not rotated about this axis. It's rotated about this axis. The symmetry axis is Z. So you will have maximum power in X hat and also in Y hat direction. In the full XY plane, actually, you will see maximum power. Do you get what I'm trying to say?
So you are saying if instead of zx we draw zy, we will get the same figure, means due to symmetry.
Yes. Right. So basically, this is the direction of, this is the axis of symmetry. So with respect to this direction, the radiation pattern is independent of phi. If phi is defined as, this is x, y, and if this is some angle phi, the usual spherical coordinates. Get it? It's not symmetric with respect to x, because it's symmetric with respect to the acceleration direction. Okay. Okay, what about the plane of polarization? What about polarization of this, right? So if you recall, the polarization direction is that E is proportional to B at B dot perp. So this is the direction of polarization. So if you're, basically this is E. So it's polarized in the plane of n hat and acceleration, right? So E lies in the plane of n hat and acceleration. So if you're sort of seeing it from somewhere else, your n hat changes, but electric field always lies in that plane, in this direction, along the direction of the perpendicular. This is the projected acceleration, projected perpendicular to the line of sight. Right, so this is the line of sight. This is, yeah, drawing is a little difficult because these are 3D, 3 dimensions that I'm talking about. But it's important to have a feel for.
So the incident radiation is
Yes.
polarized along z cap, right?
Yes. That's
and when we see it, it will be polarization along any line of sight. So
right, when we see it, it will always be polarized perpendicular to n hat, right? But it will be in the plane of n hat and epsilon hat, right? So these two unit vectors n hat and epsilon hat make a plane, okay? And that is the plane in which electric field will lie, and it will be perpendicular to n hat, basically along the direct. So that's the right, if you recall, this actually comes from this, right? N hat cross beta dot, right? And this is nothing but this, right? Okay. Yeah, you have to look up a little bit and imagine a little bit, but fundamentally this is the formula that we're using, right, for radiation electric field. Okay. Okay. So this was for a perfectly polarized incident radiation. What if your incident radiation is unpolarized? What happens in that case? So let's go to part 2. So Thomson scattering of unpolarized radiation. Okay. So what are we considering? Let's say, so unpolarized radiation, we can actually consider, without loss of any generality, unpolarized radiation can be considered as sum of any two independent linear polarizations. For example, if this is the direction of propagation of this radiation, if it is unpolarized, we can actually just choose two direction, this and this. Any two directions can be chosen according to our convenience. Any two, right? And we can have equal amplitude in these two directions for the field. The key thing is their phases are uncorrelated. So total power of this polarization and this polarization for any two perpendicular set of polarizations is equal. So this is the geometry, this is K, this is n hat. We are looking at this particular direction. Okay, and this is epsilon 1 hat. Right, so now we are given K and n hat. Okay, and we choose epsilon 1 to be in the plane of n hat and k hat. So you have some unpolarized radiation going along the k hat direction. So this amplitude and the transverse amplitude are equal. Okay, so this is the transverse direction epsilon 2. Right, so we can actually consider linearly polarized light polarized in this direction and another linearly polarized light polarized in epsilon 2 hat direction. They have equal amplitudes in these two directions, but uncorrelated phases. So we have K, the direction of propagation of both these polarizations, and n hat is some direction in which we are looking at, and we choose epsilon 1 hat to be in the plane of n hat and k hat. Okay, because we can choose any two independent linearly polarized light when we are treating unpolarized radiation. So this is your capital theta. Okay, and this is small theta, which is nothing but 90 minus capital theta. Right, these are in the plane. This epsilon 1, n hat and k hat are in the plane. Epsilon 2 hat is perpendicular to this plane. So this angle is pi by 2. Okay, good. Is this clear? What I have just said, that we can consider unpolarized light to be sum of any two independent linear polarizations, and here for convenience we choose epsilon 1 to be in the plane of n hat and k, and this to be perpendicular. So the setup is somewhat different from previous case. Previously we had chosen epsilon 1 as your z hat direction. Here we will be choosing k hat, and there is a reason for that. And the reason is, we will actually come to that. Let me first write down. So the polarizations along epsilon 1 and epsilon 2 hat are random. So what about this differential cross section due to unpolarized light? This is equal to half. So let me actually write down and then explain half d sigma d omega angle theta. This is plus d sigma d omega at angle pi by 2. So basically what I am saying is that, right, you recall our dp d omega was equal to s, the Poynting flux, d sigma d omega. Okay, so the flux is just the sum of these two fluxes, because they are they are uncorrelated. So this just sums up. So this was c epsilon e naught squared by 8 pi times 2. But if E naught is the amplitude in one of these polarizations, this is that. Okay. And what about this? This basically you can sort of think of it as if you're looking at some n hat, the power that you receive here is because of this in plane polarized light, right, which is at this angle capital theta, and perpendicular polarized light, which for which you should use theta equals pi by 2, because acceleration is perpendicular to the n hat. So this corresponds to epsilon 2 hat polarization in that direction, and this is because of, right, so this is the sum of the two powers. So that's why you have this 2 coming here. So it's half of this cross section plus this cross section. Is this clear? I'm using the polarized expressions for differential cross section for polarized light, but I'm plugging in capital theta here and pi by 2 here. And the reason for pi by 2 is that this is in the, this is at pi by 2 relative to n hat. Okay, so this, what is this? This is equal to half d sigma d omega. This was, so let me just write down r naught squared sine square capital theta. And this is just what we had previously, and this is what at pi by 2, this is just r naught squared, right? So this is equal to r naught squared by 2, 1 plus sine squared capital theta. Okay, this is equal to r naught squared by 2 sine squared capital theta is nothing but cos squared. So cos squared small theta, 1 plus cos squared theta. So this is small theta, that is capital theta. So this is your unpolarized differential cross section. Now here, so this is the direction between epsilon 1 hat and n hat. This is the direction between n hat and k hat. So yeah, so so now the symmetry axis is actually about k hat, because we have actually taken this general case where we are given just n hat and k hat, and you can choose these two polarizations, epsilon 1 hat and epsilon 2 hat, without loss of generality. So let's see. So what are the, so is this clear why I substituted pi by 2 here? Because we are looking at,
Yes, sir.
yeah, okay, good. Right, so you may have to actually read it a little bit just to absorb it. But so what are the properties? So this is the, right, if you recall, so this is the cross section. So this is d, so if you recall, so d sigma d omega polarized was what? This was r naught squared sine squared capital theta.
Sir, here the total cross section will be more. I mean, does this signify?
Let's come to that. We will come to that. It is actually the same. D sigma by d omega due to unpolarized light is equal to r naught squared 1 plus cos squared theta. This is small theta, that's capital theta. Okay. Right, so let's see. So this is, so then I'll just write properties, some of the properties of Thomson scattering. Right, so there is a forward, backward symmetry. Basically, d sigma d omega for theta is equal to d sigma d omega for pi minus theta. Right? You know, whether you are sort of looking at this direction or you are looking at pi minus theta, this is sort of like a reflection symmetry. You will have the same cross section. Okay, good. The second property is total cross section is the same actually. Sigma t for polarized is actually equal to sigma t for unpolarized. How do we see that? Let's see. Let's do this one. So sigma polarized is equal to r0 squared sine squared theta times 4 pi. Right? I mean, I'm just integrating r omega, and sine squared theta is nothing but 2/3. Right? If symmetry axis is about the direction of acceleration, what you get is 8 pi by 3 r0 squared. What about this guy? Unpolarized, so sigma unpolarized is equal to r0 squared 1 plus cos squared theta times 4 pi. Right, what is that? That's equal to r0 squared 1 plus cos squared theta times 4 pi. And what is cos squared theta average? It's 1/3. So this is 2/3. So you know, in the end you have, so this is 1 plus 1/3. No. Oh, there is a factor of 2 here. I missed it. So this is 4/3. So this, the whole thing in the end is equal to 8 pi by 3 r0 squared. Is that not right? 4/3. So there's 2/3 times 4 pi. Right. So basically this you can see from here. See, the difference here is actually slightly subtle. In this case, when you're considering polarized light, yeah, you have K and you have epsilon. Just a second. Right, and this angle theta, this angle is capital theta. And symmetry is with respect to this direction, right? Whether you see here or here, you get the same field. Okay, this was the setup here. So that's why sine squared theta, capital theta, gives you 2/3, because that sort of is like a symmetry axis. Okay, in the second case, when we consider unpolarized light, this is our K, the direction, and this is your n hat. Okay, and this angle is actually theta, small theta, and the symmetry axis is actually, you know, about K hat. So, you know, whether you see here or here or here, you'll see same power. Okay. Because you can, you know, here you're not given, your epsilon 1 hat is not given in this case, right? You're choosing epsilon 1 hat. You know, you have a choice. You know, you can have any two independent linear polarizations. So given a K hat and N hat, you can always choose in the plane of N hat and K hat. And, you know, epsilon 2 hat is, you know, just given by, it's just in the perpendicular plane. So what's given here is K hat and N hat. Epsilon 1 and epsilon 2 are in some sense in your hands. Okay, you can always choose epsilon 1 to be in the plane. That's why the you use cos squared theta equals 1/3. And that's why here you choose sine squared capital theta equals 2/3. So there's a little bit of a difference which you have to be aware of. Here, the plane is determined by epsilon and k. Here, the plane is determined by k and n hat, and epsilon is sort of in your hand. Okay. So that's why you get this. What about, is this clear? Somewhat.
Yes, sir.
Somewhat, yeah. You will actually have to think on your own, and you can ask me in the next class. What about the third? What about degree of polarization? So degree of polarization of scattered radiation. You see, the incident radiation is unpolarized. Okay, but the scattered radiation is not in general, right? For example, if you look through, if you look at direction, say, if you're looking at epsilon 1 hat direction minus epsilon 1 hat direction, in that case, you don't see this polarization, you don't see this acceleration, but you see this acceleration. It will be totally polarized in that case. Right, when you're looking through epsilon 1 hat direction, so you get full polarization. But if you're looking at, say, closer to k, you see this as well as this. You see two equal, you'll see equal accelerations in this and this direction. And since they have zero, no phase correlation, you will see unpolarized light along k hat if you see along k hat. So what is the degree of polarization? Let's see. So in plane intensity of this scattered light will be proportional to cos squared theta, small theta. Do you see that? So this is the polarization along epsilon 1. So if you are sort of at theta equals pi by 2, you should see nothing of this polarization. So this is the in-plane intensity. Out of plane, so in plane will be like along epsilon 1, and out of plane would be epsilon 2 hat. This is independent of theta, so this is constant, independent of theta. All right, then their amplitudes are actually the same. So I can actually write it as I naught cos squared theta, and this is just I naught. Right. So what is this pi, which is degree of polarization? What is that? That is intensity of basically the difference between these two intensities. So I naught 1 minus cos squared theta divided by 1 plus cos squared theta. So this is the polarized intensity, because the equal amplitude part just gets cancelled. The remaining part is the polarized intensity. So this is equal to 1 minus cos squared theta by 1 plus cos squared theta. You can actually see when theta equals 0, you get 0 polarization, right? When you're looking from here, right, you are able to see this acceleration because this is perpendicular to the line of sight, and you are always able to see this acceleration. So you see two equal amplitudes but uncorrelated phases. So this is totally unpolarized light. Right? When theta equals pi by 2, when you're sort of seeing from here, right, this epsilon 1 acceleration is along the line of sight. You don't see any radiation because of this. All you see is because of this. So it's totally polarized in case for theta equals pi by 2. Right, you get degree of polarization which is 1 for theta equals pi by 2. Okay. So this is actually important. For example, even if you don't have the original source, even if the original source is unpolarized, like starlight. So, for example, if you have a star and if you have a planet here, okay, and this star is sort of emitting black body unpolarized radiation in all directions, right? Now this planet, and suppose you're sort of seeing from here, okay, this planet you are observing, from at various phases, it's here, right? So in this case, your n hat is this directions, you have. So this radiation which goes there will have polarization in this direction and in along n hat, right? There are two, so this is k and n hat. So the charges will oscillate like this and in the perpendicular plane. So if you're looking from here, this part you will not be able to see because acceleration is along the direction of n hat. But the transverse one you'll be able to see. So you expect to see 100% polarization of scattered radiation in this geometry. So this is your k, this is your n hat, and this is sort of like equivalent to seeing from here, right? One of along the line acceleration is not seen, so you see maximum polarization here. But if it is here, for example, then this is your n hat, is in this direction, and your you are able, your accelerations are, these are the two accelerations of the incident due to the incident radiation. And since both of these are perpendicular to your line of sight, so this source at this location, this planet will be unpolarized, right? So polarization is maximum here. So if you make a plot of polarization as a function of the phase or the time, you'll see maximum polarization and it's sort of minimum and maximum, right? And it's sort of periodic with so maximum to maximum. So this will actually happen on a time period of t/2. Okay, and actually people trying to do exoplanets actually try to look at polarization and try to infer these things. I mean, this we talked about Thomson scattering, but this is generally true that if you have scattering, even though the radiation which is exciting that is unpolarized, the scattered light is polarized. So scattered light is generally polarized. Okay, and it's because of this fact that the radiation due to acceleration along the line of sight is not seen. Is this clear? Scattering is actually very, very important observational diagnostic too. Okay, where did it go? So this is about 120. So I'll actually, so the last portion of this chapter is remaining, which is basically a bound oscillator. So Thomson scattering is for a free charge which is accelerating and oscillating due to an imposed field. But sometimes, for example, in Rayleigh scattering, the charges are bound to molecules or atoms. In that case, there is also a natural frequency associated with that, binding potential. So we will actually treat that, and that's related to the formation of a line, for example. So that sort of is the last part of chapter 3. So we'll do that. So I actually encourage you to read last part of chapter 3. Chapter 4 is on relativity, and to treat the radiation, a little bit in the context of special relativity. So if you have not done special relativity at all, I encourage you to start reading about it right away. Things like length contraction, time dilation, Doppler shift in terms of the relativistic transformation. Okay, so start reading a little bit about velocity addition, Lorentz transformations, if you have not done that earlier. Okay, again, we will actually not be covering a lot of the background in that, because it's assumed that you've done basics of relativity. If you haven't, please try to brush up. Okay, so we are actually moving towards fast moving radiating particles. Okay, because in high energy astrophysics we have synchrotron radiation and inverse commutant radiation, which are essentially because of relativistically moving charges, and for that, to treat that, we will need a little bit of relativity. So I encourage you to read up. Okay, any questions? So everyone has done relativity in some form or another, right?
Yes, sir.
Okay, good. If you have not, please read up. Even simple, even the beginning material is good enough. But you need to have intuition that space and time coordinates get mixed if you approach speed of light. You have to have the physical, a little bit of physical intuition. Okay, good. So then we'll meet in the next class. I'll stop recording.